So now that we've done a minimization, let's make a directory for our K-star-based mutational scan. Change into that. We're going to set this up the same way we did our inverse alanine scanning. I'll call it round 1 with 2 ensemble subdirectories. And we'll make a directory for each one of the residues. All right, great. And now we need to grab that PDB output from minimization. So I'm going to go back, grab that PDB from the minimization ensemble output and copy it here. And I'm just going to rename that min.pdb. Okay, great. So now we're going to go through to the Osprey interface. Mine is in downloads. And I'm going to import that PDB output from minimization. I'm going to prepare it how we have already. Again, not doing minimization again. I'm going to go through and check the filter, chirality, duplicate atoms, missing atoms, bonds, and protonation. I'm then going to save this PDB and then also save the Osprey molecule as we've done before. So to prepare both those files, I've just called it minimization.omol and then minimization-prepared.pdb. So let's open it up just how we did inverse alanine scanning, this PDB and PyMol, and start visualizing some of these clashes. So I've opened up the file in PyMol, and I'm going to once again visualize side chains. For round 1, let's once again start at glycine 45, which is here. And I'm going to highlight this, highlight all the residues on the protein, action, find, once again, any contacts between chains within 4 angstroms. We are once again in contact with H301 for flexibility on this residue. So I'm going to go over the interface and prepare a design where I'll be mutating G45 and flexing H301. Once I'm in the interface, I'm going to hit File, New Confirmation Space. I'm going to navigate to that mutational scan directory and open up that Osprey molecule, which I have here. I'm going to load back in the amino acid libraries. And now it's time for mutation. So this is going to vary a little bit from inverse alanine scanning. In inverse alanine scanning, we'd load in a mutation, say for glycine 45, mutate all 20, and the rest of these would be mutated to alanine. Here for the K-star-based mutational scan, we're only going to scan at glycine 45, and we're going to leave the rest of these residues at their wild type. So I'm going to select glycine 45 for my first round, hit mutations, and I'm going to check all of these amino acid identities in the menu. Close this. Now have all those mutations selected. Edit, I'm going to go to my flexibility menu. Again, I'm going to click this residue, edit, select all. I want all the rotamers for all of the mutants. Enable ligand translation and rotation. And that residue was H301. So I'm going to go to chain Y and add flexibility on H301. So I now have my confirmation space, file, save. I'm going to save this in round 1. I'm going to save my complex, the protein ligand. I'm going to compile them and then run the K-star score. So I'm in the cluster again. I have all my files and I'll be running the K-star score, passing it the round 1 complex, round 1 protein, and round 1 ligand. That's now completed. So I can look at the output file. It has all the K-star scores. Copy these over to our Excel sheet. I have round 1, I've called it, G45 is the residue. We flexed H301. I'm going to paste these into the Excel file. Again, making a note of the difference in wild type. And the highest K-star score is going to be 20.86, which you can find right here. And that occurs when we mutate glycine to arginine. So I've inserted the difference between the point mutation of 20.87 of glycine arginine and the wild type, this top row here, gives an increase in K-star score of 1.43. So in the previously performed inverse alanine scanning, what we would do is we'd repeat this process for all 6 residues using a common OSPRE molecule, and then we would perform a combinatorial search. Now, in the K-star based mutational scan, what we're going to do is instead of using, for example, a prepared OMOL file, we're going to take this sequence here, we're going to find this PDB file in the ensemble output, and we're going to use that as an input into our round 2. We'll be mutating G46. So I have my files here. I'll change into round 1, ensembles, and this is again glycine arginine, that PDB. So we want to copy glycine arginine.pdb, and let's just move that up a directory. I'll rename this to, let's call this round 1, call it actually mutational scan round 1.pdb. So I've renamed it to mround1.pdb so it's easier to work with. And let's now open up this mround1 in the OSPRE interface. So I've opened the interface, file import, mutational scan round 1. I'm going to find that mround1.pdb, open that, and do the same process where I'll check the filter, chirality, the duplicated atoms, missing atoms, bonds, and protonation. So I've done that. I'm going to save the OSPRE molecule, save it in the round 1. I'm just going to call it round 1. I'll call it mround1. And I'll save the PDB just in case I want to look back on this. So I'm going to close this, file close, hit file, new confirmation space, mutational scan round 1, mround1.omol, open. And now we want to do mutational scan on the next residue up from the interim. So I'm going to find that PDB file in the ensemble that we just extracted, and I'm going to open that in PyMol and figure out which residues are within 4 angstroms. I've opened this file in PyMol. I can visualize the secondary structure if I like with Command DSS. Hit sequence. Again, note that now that we've done that mutation, residue 45 has been mutated from glycine to arginine. Let's visualize these side chains. Here. And next is going to be G46. Click that. We're going to highlight all the protein residues, action find, any contacts, 4 angstroms. This is in contact with H301, also in proximity to T296. So we're going to go back over to our user interface, edit, load in our confirmation libraries, get our D-peptide, L-protein, close this. And now when we go to mutations, we've already finished 45. So notice this is now again glycine arginine. We're now going to go to glycine 46, and we're going to mutate this to all 20 amino acids. We're going to again go to our flexibility menu, select all the monomers for that mutation, enable translation rotation, and those clashing residues were again T296 and H301. So I've selected all monomers for all my mutations, set ligand translation rotation, and the residues within 4 angstroms are threonine 296, histine 301. I have my confirmation space. I'm going to close this. I'm going to hit File. I'm going to save this complex. I'm going to save this actually in the round 2. This is round 2 complex. and to protein. And I'm going to compile all of these and run the K-star algorithm once again. I'm going to repeat this process again using the previous round with the highest K-star score as input to the next round. So I'll find the highest mutant for G46 and use this as an input to check at G47. I'll continue repeating this process until I reach tryptophan 50. At that point, I should hopefully have found a ligand that has a higher K-star score than what we started with, and that outcompetes the endogenous ligand.